Please, that'd be great. Okay, so welcome everyone, and thank you for joining. So our speaker, as I'm sure you've all realized today, is Dave Brain from Colorado, who's an expert on planet atmospheres, especially with respect to their evolution and their potential habitability. Dave did his PhD and his first postdoc actually at Colorado, before hopping over the Rockies to Berkeley, and then hopping back to Colorado, where he's an associate professor. So today he'll be talking to us about whether habitable worlds require magnetic fields. So Dave, thank you very much for agreeing to come and speak to us virtually, especially given the time difference. We really appreciate it. So whenever you're ready.
Yeah, no problem. And thanks a lot for having me. So the entire time that we're together today, I'll be talking about things that are related to this 6-word question in the title. And as I've progressed through my career, I've started to realize that when the question can be expressed in one line, it feels like a more fundamental thing to be thinking about. This may not always be true, but in this case, I'm excited to have spent a couple years now thinking about this question as part of my research. So this question has to have an answer, and it could be empirically that we're done in just one slide. If these 3 planets that are artists' renditions are Earth, Venus, and Mars, then Earth has a global magnetic field while Venus and Mars do not. And Earth is habitable, we know that, and Venus and Mars could be on the very hairy edge of habitability, but in general are not robustly habitable. So empirically, the answer is yes, habitable worlds require magnetic fields. And so I will take questions for the next 50 minutes. Or I will keep talking. Okay, let's do that. So let's start very simple, hopefully not condescendingly simple. But there's a chain of logic from magnetic fields to habitability that has several assumptions built into it. So habitability, or having life on a planet, requires liquid water. If we're using Earth as our experience, to have liquid water on a planet, that requires a robust atmosphere. And there are arguments that suggest that a robust atmosphere requires a magnetic field for that planet. But some of the assumptions that are built in are that the life must be like all life that we know on Earth. All of the 6 million species or so require water in liquid form. So we're automatically constraining ourselves by drawing this diagram in this way. Also, when we talk about liquid water requiring an atmosphere on a planet, we're really talking about life at the surface or above the surface. So we're excluding incredibly interesting worlds in our own solar system that are likely to be habitable and outnumber worlds that are habitable at their surface, places like Europa or Enceladus, and icy moons in the outer solar system with subsurface oceans. And then the connection between atmosphere and global magnetic field implies that a global magnetic field shields the atmosphere and prevents that atmosphere from being stripped away to space. So confirming or disproving this link has implications for a wide variety of disciplines. So people who study Earth and the history of habitability on Earth, planetary scientists and space physicists like myself, and also for exoplanetary topics, which is driving lately the urgency of questions like this. And then a disclaimer before I go too much farther is that for the remainder of this talk until the very end, I'm going to neglect the influence of magnetic fields on things like the surface radiation environment of a planet, which can influence habitability, and also the influence of magnetic fields on atmospheric chemistry, which that link is real, although it's non-intuitive at first. So let's stay with this diagram for just a few more slides as part of the introduction. Somehow I picked the most complicated looking phase diagram for water that's available on the internet. Really, all you need are the solid, liquid, and vapor regions. You don't need all these extra ice things for what I'm about to say, but this connection between liquid, water, and atmosphere, when you're talking to, you know, a primary school student or something like that about why an atmosphere might be important for liquid water, most of them would immediately start thinking about temperature, an atmosphere providing warming that can provide the right temperatures for liquid water. But the phase diagram tells us that pressure is important too, and may in fact be more important here for the connection between atmospheres and habitability. Because in this phase diagram for liquid water, if I put the range of conditions at the surface of Earth, Mars, and Venus, the difference between Earth and Mars is very telling in terms of the importance of pressure. On Mars, the average temperature is well below the triple point of water, and the coldest temperatures on Mars are very well below the triple point of water. But at the equator on Mars and sort of low-lying areas, impact craters and things like that, on a warm summer day, it gets up to 30 degrees C or something like that. So the temperature is just fine on Mars, but the fact that there's about 0.5% of the atmospheric pressure on Mars means that it's, only liquid water is not stable for long periods of time globally on the surface, unlike at Earth. For Venus at the surface, water is supercritical at that point. So everything gets messy, and the utility of water for life in the supercritical regime is actually highly questionable and is no longer dielectric, things like that. And lately you've heard about the possibility of life in the clouds of Venus, and that's because up higher in the clouds, you actually get closer to Earth-like conditions. You get to about 1 bar of surface pressure and temperatures that are in the liquid range here. So the cloud tops of Venus are actually a much better place to be thinking about life in terms of the phase diagram of water. They're incredible challenges in other ways. Okay, another part of this this chain of logic is from atmosphere to global magnetic field, and this is where I'll spend the rest of my time, and this is where my research expertise is. There are many different ways that a planet can lose atmosphere. When we use the phrase atmospheric escape in planetary science, that's a catch-all term that captures about 6 or 8 different physical processes that require different sets of equations and different assumptions, different regimes. There are people that spend their whole career thinking about just one of these processes for a handful of planets. So to do it in one slide is doing it an injustice. But there are processes like thermal escape. Just because you have a distribution of temperatures, maybe a Maxwell distribution of temperatures of an atmospheric species at the top of an atmosphere, some of those particles are going to be above average in terms of their energy, and therefore have sufficient energy to escape the planet. You can also have sunlight drive chemical reactions that are exothermic, and those chemical reactions therefore will give some particles enough energy to escape a planet. This is important for species like oxygen or sometimes even nitrogen, whereas thermal escape is usually only important for hydrogen in our solar system. Sputtering happens when particles go crashing into the atmosphere, like a cue ball on a billiards table, hitting other balls away. When you get a particle with a lot of energy crashing in, you can sputter particles out as a result. And the yield factor for some of these types of interactions can be 100. For one particle going in, you can splash 100 out because it has so much energy. And where I'm going to spend most of my time is on ion escape. A lot of these processes up here assume the particles are neutral, but the tops of atmospheres are ionized. At least some significant fraction of the atmosphere is ionized near the top. As soon as they become ionized, magnetic fields and electric fields become important for governing the motions of those particles. Ion escape may be the only way to get out certain species that are heavier than hydrogen. It can remove oxygen, but it can also remove things that can't be removed photochemically and are very difficult to remove via sputtering, things like carbon dioxide as well, that are massive. And so the connection between magnetic fields and atmospheric escape largely comes down to its influence on ion escape, although there are indirect effects on these other processes as well that I won't go into right now. Then during things like solar storms, all of these processes may be elevated. And that would be solar storms in our own system. But for exoplanets orbiting active M-dwarf stars, for example, this is the steady state, the disturbed environment, the storm type conditions are what are happening all the time. And we're still trying to learn and figure out how each of these processes responds to very active stars. So some simple physics. The assumption is that magnetic fields should protect atmospheres. That's been the assumption for decades. I learned this as a grad student, and it's the canonical wisdom. And the reason that's so is because the physics are very simple and straightforward. A magnetized planet deflects solar wind charged particles coming from the sun, and it does this far from the atmosphere through the Lorentz force. The particles have a velocity, the magnetic field exists, and V cross B is how those particles move. And so they get deflected away from the planet. This means the solar wind doesn't encounter the atmosphere of Earth directly, and that means there's less energy being imparted to the top of the atmosphere. If that's the case, the atmosphere can't escape efficiently. In contrast to a place like Mars, where the solar wind directly impacts the upper layers of the atmosphere, and those particles and the energy are deposited directly into the planet. There's evidence that supports this hypothesis that magnetic fields should protect atmospheres. This diagram doesn't really have an x-axis. In some circles, that's called a Caltech diagram, but the y-axis is physical. It's a D to H ratio. And so it's deuterium to hydrogen in the atmospheres of various solar system objects. And Jupiter and Saturn and the giant planets, we think have a primordial D to H ratio, the D to H ratio, in the solar nebula as it formed. Earth has an elevated D to H ratio, so it's enriched in deuterium, but Mars and Venus are even more enriched than Earth. And D to H behave chemically in the same way, but they have different scale heights, different abundances at the top of the atmosphere relative to each other. And if the atmosphere is being stripped away from the top, H is going to be stripped away more readily than deuterium, leaving an atmosphere enriched in deuterium. So a chart like this is inferred to mean that Mars and Venus have undergone more atmospheric escape over the last 4.5 billion years than Earth has. And this is consistent with the idea that Earth's magnetic field is inhibiting atmospheric escape. Another piece of support comes from a postdoc of mine who analyzed escape measurements from Mars. So we have an orbiting spacecraft at Mars that directly measures ions that are escaping from the atmosphere in situ. It's a particle sniffer, a particle detector. And these observations are colored according to the flux of ions leaving Mars, and the arrows show the energies of those ions. And in a different talk, I talk about all the different channels and mechanisms that are removing ions. But for this slide, really what I want to say is Mars lost a substantial amount of atmosphere over time and is still losing atmosphere today. When we take these observations and their sensitivity to the solar drivers and integrate them back in time and couple this with all the other processes that are happening at Mars, Mars could have lost half of an Earth's atmosphere or much more than that over the history of the solar system. So Mars has a lot of atmospheric escape. The other side of the question has come up in the last decade, I would say, and this is the idea that magnetic fields should not protect atmospheres. The reason this is coming up is very unfortunate. It's because it's simple physics, and so it's going to be hard to decide between these two choices. The physics is relatively straightforward here, and this is the sails on a ship idea. Yes, you have a little planet here with an atmosphere that's escaping, but a magnetic field makes that planet have a much larger cross-section that appears to the solar wind that's coming towards the planet. That means the magnetized planet can capture more momentum and energy from the solar wind. And you don't need to have the particles directly impacting the atmosphere. If you can get some of the energy or momentum from those particles, that energy and momentum can be transferred down the magnetic field lines to the atmosphere. This is through something called Poynting flux, and the energy can be transferred to the atmosphere along magnetic field lines. We know that this happens at Earth, and we have incredibly beautiful visible reminders of this happening at Earth in the form of aurora. We also have spacecraft measurements of ions being accelerated upward, out, away from auroral zones. Hydrogen and helium, but also oxygen as well. And it's an open question what fraction of that oxygen actually escapes the system versus being trapped in these magnetic field lines over here and rattling around and ultimately re-impacting the atmosphere. But this idea is that maybe magnetic fields don't provide such a shield after all, and they could actually decrease atmospheric escape compared to the situation where this planet lacks a magnetic field. Another piece of evidence that comes up is less cartoony and pretty, but very profound. With a spacecraft called FAST, you can measure the Poynting flux in the solar wind, basically the energy input that's coming from the solar wind towards Earth. And you can measure it at the same time that the spacecraft is measuring the amount of ions that are leaving the planet through the auroral zones. This is called ion outflow. And these two things are generally correlated with each other, which tells us that the atmospheric escape at Earth responds to the solar wind. The solar wind tells the atmosphere how much to escape. There's an asterisk here, which means I'll come back to this point a bit later because there are some complexities here. But at face value, this is taken to mean that the magnetic field maybe doesn't protect the atmosphere so much. And this is energy in and ions out. I should have clicked to that right away. Okay, another one, and you don't have to absorb or understand any of these diagrams. It's just to add color to the slides. The important things are the numbers here. Venus, Earth, and Mars, surprisingly, all lose roughly the same amount of charged particles today. At face value, the escape rates are within an order of magnitude of each other, and maybe less than an order of magnitude of each other. You can see that the measured escape rates are dependent upon either spacecraft or instrument or orbit of the spacecraft or investigator or data selection technique. But in general, if Earth was losing a lot less atmosphere than Venus or Mars, you might expect the escape rates to be significantly lower than Venus and Mars, and it appears that they're not. Again, there's an asterisk here. So hopefully this is the only shameless advertisement in the talk, although I will show work from my research group. We've recently gotten funded from NASA a team science center. And this is my first foray into leading something like this. And it's been really fun so far over the last 6 months. We asked NASA to allow us to investigate this question because it's an interdisciplinary question in a variety of ways. It involves people with terrestrial experience, planetary experience, and exoplanetary experience. It involves space plasmas and planetary science and atmospheres. It involves observers and modelers. And these communities in general have started to diverge from each other over the last 30 years. And so pulling people back together and asking them to collaborate on a question of common interest has been really fun. And some of the challenges come from team building and getting people to use the same language, getting people to trust each other, getting people to realize that they were just talking about the same thing when they were using different jargon terms and things like that. And so this is what this is our team right here, and we're all working together right now for at least 2 years. So NASA gave 9 teams seed money for 2 years. At the end of those 2 years, they're going to down select to 3 teams, and then we will get more money and 5 years to continue investigating our question. So let me talk a little bit about the kinds of approaches that we could use to answering this question. Do magnetic fields matter for atmospheric escape? And one is to compare observations of Venus, Earth, and Mars. And so sometimes when you're thinking about climates of Venus, Earth, and Mars, this is called the Goldilocks problem. And so that's the reason for the visuals on this slide. And the same can be true, said when we're thinking about atmospheric escape as well. So the first is to go back to one of the asterisk things from before. When I said Venus, Earth, and Mars all have the same escape rates today, we believe that that's not an apples to apples comparison. And that's because Venus, Earth, and Mars occupy different parts of the solar system. In this model here, this is a magnetohydrodynamic model for the solar wind flowing through the solar system. The sun is at the center, Earth is over here to the right, Venus is up here, and Mars is over here. And this was run during a solar storm period. But the general idea is that some planets are close to the sun, some are far, they're at different places at different times. And so if the solar wind is what's driving ion escape, Venus, Earth, and Mars are not subjected to the same solar wind. The diagram at the right makes this point more quantitatively, where we took observations from different spacecraft orbiting these planets that were measuring the solar wind, the velocity of the solar wind, the density of the solar wind. And there's some overlap at Venus, Earth, and Mars, but the distributions that they experience over long periods of time is different. So if we want to really know if the atmospheric escape rate is different at these three planets, we have to correct for these biases. So we've started to do this, and with just a couple of studies, there are over 100 studies of atmospheric escape at these three planets, but we've just picked 3 or 4, including 2 from my postdoc. And he, with his PhD advisor, has put together a review paper where he just has one figure to start this study. And what he's noticed is that even though the escape rates are roughly similar between Earth, Venus, and Mars, the response of the 3 planets to the solar wind is different. So here I've highlighted in the solid colors the response of the 3 planets during high extreme ultraviolet flux from the sun, so solar maximum conditions. And you can see that Mars has a complicated response in terms of atmospheric escape as a function of solar wind dynamic pressure. Venus has a limited range of pressures that we've experienced when we've been there, so it's hard to tell if it compares directly to Mars or not. And Earth has a very strong response to solar wind pressure. And maybe this is because Earth has a magnetic field and the other 2 planets do not. So I said that there are lots and lots of studies. This is kind of a mundane thing that our group and our center is tackling, but nobody's ever compiled all these before. And so I have an undergrad who was really enthusiastic about this task, which is great because nobody else was. And so she started to put this all together, and we think we're going to get her a publication out of it if we can pick a couple things from these studies for her to extract and compare. But the rest of our team is starting to use this database. Those are old studies, but new studies are being released regularly. So here's one that someone from our team is involved in. And for comparison, I've put this previous plot of Poynting flux in versus ion escape out from Earth. This is from the FAST spacecraft, and this was from a single event, a single solar storm period, more than a decade ago. While some other investigators have gone back, and for this same period, they've reanalyzed the data. And so this plot right here could be thought to come from the plot at the top left of this new diagram, the study that was just released this year. And the main takeaway point is that, yes, Poynting flux is correlated with ion escape. But if you look at some other things like electric field amplitude, electron number flux, electron density, those things are correlated too. So it seems that atmospheric escape at Earth responds to many different things. They're all correlated with atmospheric escape. And so teasing out what the root cause is going to be difficult. It's going to require us to understand the microphysics in more detail. And I will also say that it's very easy to see correlations when you use log-log plots that have large scales. These correlations could be very tenuous and coincidental. We realize that, you know, things may be looking obvious there that aren't so obvious. A second approach would be to focus on Mars, which is where I've spent much of my research career, especially early on. And Mars is a fascinating place to study. And much of what we can learn about this question comes from a spacecraft that's still orbiting there. It arrived at Mars in 2014, and it's called MAVEN. And the whole purpose of MAVEN is to measure and understand atmospheric escape from that planet. And we have 9 different instruments on board and 10 or 11 different investigations, because we can use some of the spacecraft engineering data to help us in our science as well. I have given 7 90-minute seminars on MAVEN, each on a different topic as part of a graduate class. I will spare you that now and just try and give you a few slides of flavor, but I do want to convey that there's tons of exciting science here and new discoveries. So the thing that I'm going to focus on here is the fact that even though Mars lacks a global dynamo magnetic field, it has crustal magnetic fields entrained in the outer 40 kilometers or so of the crust of a 3,400 kilometer radius planet. And these magnetized regions of the crust are sufficiently strong that the magnetic pressure from those regions pokes out above the thermal pressure provided by the upper atmosphere of the planet. They're sort of locally protected pockets of atmosphere on Mars because the crust is magnetized. Not only that, magnetic fields can reconnect and open or close. And since Mars is a spinning planet, this is happening all the time at Mars. Magnetically, I think Mars is much more similar to the sun than any other object in our solar system, although the scale of that magnetic field is very, very different. This means that you can have processes that happen on Mars that are terrestrial in nature, like aurora, and we do see aurora happening at Mars in the crustal fields. This is a built-in control experiment for the question that's the topic of this seminar, because when you compare Earth to Mars, maybe the magnetic field is the reason for any differences we see between those planets, but it could also be that the 2 planets are different size or have different atmospheric composition. So it's very hard to have an experimental control. But at Mars, you have unmagnetized and magnetized regions on the exact same planet with the exact same atmosphere. So if you can understand atmospheric escape in these 2 regions distinctly, you can isolate the effects of the magnetic field. So this is something that my group has been tackling. To jump to a result right away, you might think that since the crustal fields are not uniformly distributed around the planet, they're stronger in some regions than others, that as Mars spins on its axis and rotates, we would expect atmospheric escape to vary up and down if those magnetic fields are having an influence. And globally, when we take the global atmospheric escape rate as a function of the location of those really strong crustal fields, when they're located at midnight versus noon, we see some variation, but that variation is smaller than the uncertainty in our measurements. The inference is that escape doesn't vary as Mars rotates. These crustal fields are not influencing the overall atmospheric escape in a significant way. We can look further at that, and instead of looking at the global escape rate, we can try and zoom in and just look at the escape rate above magnetized and unmagnetized regions. So now when I plot our escape as a function of geographic location at Mars, at an altitude of 0.6 to 0.7 times the radius of the planet, so 1,000 kilometers, maybe 2,000 kilometers or something like that, we don't see really any variation in the escape with geographic location, which suggests that the crustal fields aren't having an influence. Magnetic fields don't matter. However, when we go to lower altitudes, things start to get statistically hairy. So there's some places where there are more planetary ions, oxygen ions going towards the planet than there are moving away from the planet. And this is just because we're undersampled in each one of these bins. But you start to see a hint of the crustal fields near 180 degrees. This isn't anything that I'd run to publication with. This is only suggestive. However, when I take this map and I separate it for the day side of the planet and the night side of the planet, it starts to become much more apparent. The strong crustal fields in the southern hemisphere are 180 degrees. They're darker blues here. And in the northern hemisphere that's unmagnetized, they're really light blues, low escape flux. And that switches on the night side of the planet. So it seems like when the crustal fields are exposed to solar wind, escape increases from those regions. And when they're hidden from the solar wind, having those protected pockets of atmosphere decreases escape. So there's some interesting things happening at Mars that we're still trying to figure out. And my initial assumption that the magnetic field doesn't matter, when I went deeper into the analysis, it's starting to seem like maybe it does. One last thing is from a PhD student who just graduated in our group. He took the same kind of analysis, but instead of organizing it geographically, he organized it by the strength of the magnetic field at a reference altitude. I'm not going to take you through all 4 panels, just one. So the top left one is the flux of molecular oxygen away from the planet as a function of magnetic field strength. And when the magnetic field strength is low, it really doesn't matter what the magnetic field strength is. On the planet, you get the same fluxes of oxygen at the same altitudes. But when you start to get into regions where the magnetic field on the planet is strong, that magnetic field appears to affect the flux of oxygen away from the planet. So he's starting to see some of the same things that I was seeing in my analysis, that the magnetic field does influence how charged particles are moving away from the planet. The magnetic field appears to matter. Whether it matters in a global or net sense is something that we're still working out. And you can see the same trend for atomic oxygen as well. So let's move here to the next section. Modeling is another way to approach this question. So we tried to get a control experiment with Mars, and the answer there is complicated, and we're still working on it. It is, of course, important to compare the escape rates from the 3 different planets. But if you can appropriately understand your physics, then maybe the best control experiment you can build is to put a planet in a box and model it and slowly turn up the strength of the magnetic field of that planet to see how things respond. So on our team, we have people who model exoplanets, and Ofer Cohen is one of them, who has an MHD model, magnetohydrodynamic model, for how planetary atmospheres interact with a flowing solar wind. But he's just one modeler on our team. We have people from the unmagnetized planetary modeling community, people from Japan, people from the US who use MHD models, and then people in my group who use models with more sophisticated physics that comes at the expense, that comes at great computational expense. So we can't model very many situations because it takes so long, whereas these groups can model lots and lots of situations, and their models seem to match observations in our own solar system. So we have a variety of tools. We also have people from the terrestrial modeling community, and this community has greatly diverged from the planetary modeling community over the past years. And so we're happy to have these groups now talking to each other again. So Alex Glosser is someone at NASA Goddard who has MHD models for how atmosphere escapes from Earth. And the modeling approaches for unmagnetized and magnetized planets are very different from each other. Unmagnetized uses a fully self-consistent approach where there's a neutral atmosphere that gets ionized in the model. And those ions move in the model directly out of the atmosphere, and everything's modeled self-consistently. At Earth, the field strengths are so large that that brings the model to its knees if they would try that. So instead, the model doesn't go all the way down to the atmosphere. It only goes partway down to the atmosphere. And then they have to use scaling laws and relationships to get between the atmosphere and the lower boundary of their model. But there are pros and cons to both approaches, and we're merging them right now. So one random example that I'm going to pick is not really random. It's from my group. I'm deciding to advertise my group. But I feel totally okay about that because this was also a PhD student. So she took our model and she turned off the magnetic field in the model, which is the default state of the model. And one chapter of her thesis was to put a global magnetic field in and to dial up its strength. Really strong magnetic fields like Earth, again, would bring this model to its knees. So these are really weak magnetic field strengths. But if she dials up the strength, you can see the change in morphology of the magnetosphere of the planet. It's a very different looking beast as you increase the magnetic field. That structure, in turn, leads to differences in atmospheric escape. So really, the big takeaway plot from her paper is this one. As a function of magnetic field strength, it turns out magnetic field influence is complicated. There's an intermediate magnetic field strength that maximizes escape rates from the planet, which is not really what anybody expected. We expected this to either monotonically increase or monotonically decrease as a function of magnetic field strength. Magnetic fields should either decrease atmospheric escape or they should increase it. It shouldn't be complicated. So we're really mad about this result because now we have extra work to do. However, there are some physical explanations for this. When the field strength is too low, any escaping particle could be redirected straight back into the planet. And it turns out having a little bit of planetary magnetic field there gives you these sort of auroral regions or cusp zones where particles can start flowing away from the atmosphere, get away from the planet before they escape. So having some magnetic field strength is useful. Having too much is harmful because then when neutral particles become ions, they're embedded deep in the planet's magnetic field and they just rattle around on these magnetic field lines and never leave the planet at all. The caution here is that we're still in a regime that's very different from Earth's magnetic field. So even more physics can be added to the explanation as we dial up to higher magnetic field strengths. And right now we're computationally limited. And one task of our center is to start to overcome those computational limitations. And this is to make that point. This is the previous result from my student, but this would be Earth's magnetic field strength way over here on a log scale for magnetic field strength. So we're still far away. However, there's some evidence that our results agree qualitatively with those of others. A group in Japan earlier this year got basically the same result, that at an intermediate magnetic field strength, you maximize escape, and then it decreases again after that. And if we had been paying close attention almost a decade ago, we would have noticed this paper from Earth. This isn't atmospheric escape on the y-axis. Instead, it's Joule heating power when charged particles are kind of colliding with neutrals in the atmosphere and things like that. But Joule heating is pretty analogous to atmospheric escape or outflow from planets. It's been subsequently shown. So if we had put 2 and 2 together, we would have noticed this modeling result, which has the same qualitative trend. Okay, so where to? And I got an, let me see how I'm doing on time. Oh, I think I'm doing okay. I have 5-10 minutes, is that right? Okay. So what's next? What are we working on now? What can be done? So many things can be done. We're going to continue these apples to apples comparisons of escape at Venus, Earth, and Mars. And so the plot here at top right shows maps of escaping ions from all 3 planets from a single spacecraft. And we want to pull in as much of this data as possible, correct for instrumental effects, correct for spacecraft orbit effects, and correct for external conditions at the planets to really understand the differences in escape at these 3 planets. As I mentioned very recently, we're working on developing a merged simulation, big global simulation for understanding planetary ion escape. And this is a risky task that might fail. But we were told that one aspect of team science is to think big and take on risk and try. Also, we're working at a much more fundamental level about understanding from a chalkboard or a whiteboard approach how atmospheric escape works. Since the communities have diverged, there's really no unified understanding of how escape works from unmagnetized and magnetized planets. There have been some flow charts like this for Earth that show that you start with electron heating, and that changes the scale height of electrons, which increases an ambipolar electric field, which causes ion upwelling, which causes waves. This is theoretical understanding, but only some parts of that system have actually been measured and correlated with each other. We'd like to come up with a unified understanding of all the processes that are important for atmospheric escape, not just for charged particles, but for neutral particles as well, and make that comparison quantitative across multiple bodies. Another issue with a problem like this is people tend to get siloed into their own planet. I've been mostly a Mars person for my career, but to answer this question, I'm having to become a Venus person and an Earth person and an exoplanet person and a giant planet person as well, which is really fun. It's fun to feel like you're growing at this stage in your career. We want to consider neutral particle escape and giant planets and small bodies like comets too. Comets are maybe the most visible reminder that we have as a species that atmospheres can escape. It happens anytime a comet gets close to the sun. You can see it in the sky, and if you have the right filters, you can see different kinds of escape happening from a comet, plasma escape and dust and neutral escape as well. Again, I mentioned in the beginning that we weren't going to talk about the surface radiation environment or atmospheric chemistry, but that has to be folded in as well if we're really going to talk about habitability. And I have some ideas about what the effects of each of these things are that I'm happy to address. And finally, there's another team science center in the US that's thinking about atmospheric source processes on exoplanets, outgassing from interiors, magma oceans, things like that. And we've started talking to each other to build up a unified understanding of exoplanetary atmospheres. So I'm not done with this slide. I have 2 or 3 more. I haven't talked too much about the exoplanet connection, but we have exoplanet people that we're interacting with as well. And we're just beginning to be able to detect magnetic fields at giant exoplanets, Jupiter-size exoplanets. And those detection techniques are still controversial in their interpretation. But we're getting to the point where that's possible. It might be possible in the next 10 years or so to confirm more of these detections and maybe even extend down to Neptune-sized planets. Detection of magnetic fields at Earth-sized planets is probably 50 years off and requires some space-based radio telescope or something like that, unless something ingenious comes up for exoplanets. And this is a field that's 25 years old, and we've progressed way farther in 25 years than I think anyone expected we would. We're also definitely detecting atmospheric escape from exoplanets. So the transit technique for exoplanets, you can see the transit here, this black line, when the physical planet itself passes in front of its star. You can see how much of the starlight is occulted. At UV wavelengths, however, the transit is incredibly deep and asymmetric. And this is because hydrogen is escaping from the planet, and it's escaping from the planet in sort of the shape of cometary escape, where there's a leading edge to the escape and then a long tail. So we can see in multi-wavelength transits that atmospheric escape is happening. So a big question for this community is, can we assume that exoplanetary magnetic fields improve chances for habitability? Should we be striving to detect whether those magnetic fields are present? And it's still assumed, this is from 2015, but you can see a press release at least every 3 months that will have a sentence like this, that a planet's magnetic field protects the atmosphere from being lost to space. The canonical wisdom is still the canonical wisdom, even though it hasn't been demonstrated yet that this is true. So here, 2019, in our own solar system, based on MAVEN results, the mission that I work on, there's a press release that says the magnetic field of Mars disappeared and the solar wind stripped the atmosphere away. We know that Mars lost a lot of atmosphere. I'm willing to say that. We don't yet know that the loss of a magnetic field at Mars was the chief cause of this. So with that, hopefully I've conveyed that A, this is an exciting problem, B, there are a variety of solutions, and C, it's complex, which leaves us with a lot of exciting physics and astronomy to do. So I'll stop there. Thanks a lot.
Dave, thank you very much. That was a really, really excellent talk. On behalf of everyone, I'll kind of lead the round of pausing. It's difficult virtually, but I'm sure there'll be a lot of clapping if we were in person. So I imagine there'll be quite a few questions. Who would like to kick off?
Can I ask something? Sorry. Oh, sorry.
Oh, whichever order. I think maybe. Yeah. Do you want to go?
You mean me?
Yeah.
Okay. Sorry. Could you go back to the graph where you show that Sorry, I just kind of lost my question. Could you just go back a few slides and maybe I'll remember?
Yeah, no worries. Modeling
yeah,
this
this one.
Yep.
So the next one, sorry, where you show with Earth as well, the comparison with the magnetic field strength. So I was just wondering, what about the escape rate for Earth? How does that compare if we have an estimate of that?
Yeah, so the escape rate for Earth is way up here.
So it's also a lot higher.
Yeah, it's also a lot higher, and that would suggest that this curve should turn around. But I'll also say that I glossed by some of the caveats in this model. I mentioned that this model has much more sophisticated physics than MHD, but it has a boundary condition that is much less sophisticated than the MHD models. So we tend with this model not to be so confident about the absolute escape rate coming from the model, but we're much more confident about relative changes in the model as we change external conditions or change the strengths of the magnetic field. So we tend to focus on relative changes rather than the absolute number. But if this absolute number is correct, then this curve needs to turn around again at some point, which suggests we get into some new physical regime.
Oh, okay, thank you. That's really interesting.
Chris, you're next.
Yeah, so I'm wondering about the sensitivity of these results to solar wind conditions. So, I mean, there's obviously solar cycle variations, but just, you know, amplitudes of turbulence and shocks will vary with distance to the sun, for example. So I'm wondering if you have any comment about that.
Yes, so the two comments. One is we're investigating this right now with the models. And so I have a new student that's taking this exact same thought experiment and doing it for a different orientation of the magnetic field in the solar wind and trying different angles, because the global magnetic field of the planet has a certain magnetic field orientation. And so that can reconnect with the magnetic field in the solar wind and either open up the magnetosphere or close it up. And she's finding that it does change the shape of the curve. It moves the curve up and down, but it's not changing the, it changes the calibration of the curve. It moves the curve up or down, but it doesn't change the shape of the curve. It still suggests that the magnetic field, there's some intermediate magnetic field strength that's important. At the same time, that's just one part of the solar wind. It can be the solar wind pressure, the solar wind Mach number, and these all do have an influence on escape. And so the idea is that the external conditions shift the curve up and down, and the magnetic field controls the shape of the curve. But we're still in the process of verifying this.
Thanks.
Stuart?
Oh, yeah, Dave, that was great. Thanks. I wonder if you thought about how what you learn here might map out to other kinds of stellar winds, you know, to older stars that have higher mass loss rates, or dust-driven winds, or that sort of thing.
Boy, yeah, we're starting to think about it. So within the solar system, since people tend to be siloed within their planet, a lot of those studies focus on the solar wind conditions and the sensitivity of loss to changes in the solar wind. And so there's been a dearth of literature that compares between objects or focuses on the characteristics of the planet itself, the size or the magnetic field. So initially we've been starting there, feeling that a lot of has already been done on this first question. But now as we get into this, we realize we have to bring that back again, especially because many of the exoplanets that are being detected are around M-dwarf stars, which are smaller, but especially young M-dwarfs, are highly active. And so the infrequent situation in our own solar system of an active period or a solar storm or a CME is the norm around these systems. And what I've modeled here and what I've shown in the observational results tend to be quiet time results. Because the disturbed time period, we don't have a statistically significant sample of what's happening. But that's the usual situation in these other systems. So we need to fold that in, but it's going to push the regime, to an extreme. Dust-driven winds, that's tough too. We don't have the expertise on our team to think about that, but maybe we need to incorporate it because there's a lot that can happen there as well. When you have dust, you can't cross out any term in your physics equations. All the terms matter at that point.
Right. Thank you.
Sasha?
Yeah, my question is, sorry, it's known that outside of magnetic field shield, nobody can survive more than half a year. Is it correct? So in other words, okay, can you say a few words about protection of, with the help of magnetic field, protection of the planet from high energy cosmic rays?
Yeah, sure, I can. So for the various kinds of harmful radiation that can reach a surface, the magnetic field is most important for particles as opposed to photons. It's not important for photons at all. It's important for energetic particles. And it can shield the surface of a planet from those energetic particles. For some intermediate energy, the atmosphere is also important for shielding the surface. I got my brain tied up in a knot. Hold on a second, let me untangle it and go back to the original question. For ionizing radiation at the surface of a planet, the magnetic field can be important for preventing ionizing radiation from reaching the surface of a planet. In terms of understanding the influence of a magnetic field on preventing the ionizing radiation from reaching the surface, it's a fairly straightforward question. The stronger the magnetic field, the less radiation reaches the surface. So the complexity of the question isn't very great, but nevertheless, it's an important effect for making a surface habitable. The atmosphere does provide some protection from the radiation that can reach a surface at some energies. And there's some evidence that the radiation that reaches the surface at the energies that the atmosphere can shield from is particularly important for cell damage and things like that. It's not the most extreme energy particles that are the most important, it's these intermediate energies. So it becomes more complicated when you add the atmosphere into the mix as well. So we haven't addressed that in our group because we only have seed money for 2 years. So we had to pick a subset of our questions to focus on in the first 2 years. But our plan is that if we get to continue, then we'll start to pull that expertise into our team and fold it into our thinking.
Thank you. Thank you very much.
Does anyone else have any other questions? In which case, I'll maybe ask one. So so David, I think you touched on this a little bit in when you were answering Stuart's question, but the sort of the evolution in time of the activity from the host star in the or the sun or a host star for exoplanets, the activity level will kind of be high to begin with, and then it will, depending on the mass of the star, either sort of stay high and then drop, or drop kind of reasonably quickly over time. Is that something you're planning to sort of factor in terms of trying to answer the question of habitability of planets or exoplanets that might be in the habitable zone now? Kind of what bombardment in terms of flares, CMEs, stellar winds that they've been sort of subject to?
Yes, absolutely. And we're starting this already. So a couple comments here. One is, I mentioned that young M dwarfs especially are very active. It's an open question about middle-aged or advanced age M dwarfs. That seems like some fraction of those M dwarfs are active, but there could be a large fraction of those that are even less active than our sun. But for the active ones, you get a double whammy, because they're more active, you have more storms hitting your planet. And for that planet to stay in the habitable zone, it has to be even closer to the star than in our own system. M dwarfs are small and cool, so everybody gets closer to the campfire, but then the campfire is spitting out sparks, and you're more likely to get those sparks crashing into you. So it's a tough environment, M dwarfs. I can't wait for the day that we are focused on, G stars or something like that. I think that's maybe a better environment for atmospheric escape, but I still think it's possible for planets around M dwarfs to retain significant atmosphere. The experiment that we're doing right now is for early Mars, because as Stuart mentioned and you mentioned, the rotation rate, the history of the rotation rate of the star, and therefore the mass loss rate of the star, is important. And currently we don't understand the history of the rotation rate of our own star. We have 3 different paradigms for what that could have been as a function of time, which means if we're going to consider what mass loss was, or atmospheric escape was, from the terrestrial planets 4 billion years ago, we have 3 different sets of assumptions, 3 different sets of external conditions that we have to employ. So we've started a model challenge activity over the past year with some of the same groups that I mentioned in this talk, all running their models for these 3 different mass loss rates from the star to see what happens. So we're working on it already.
I think that'd be really interesting what the results of that will be. That's great. Okay, does anyone have a final question?
Yeah. Can you hear me?
Brilliant. Yeah.
Yeah. Hi. Yeah. Thanks. That's really interesting seminar. It's a great subject. I want to go back to this question about stellar activity, and thinking about the problem of when you, like for the M dwarfs, where you say you have, continuous high activity. So you're essentially like in the solar system, but let's say it's solar maximum always. I mean, the question is that with a lot of the modeling that one waits for some kind of steady state, that the success of your model is that it reproduces a steady state. But I'm just wondering, if you actually go for a system where essentially the upstream conditions are always changing, you're always putting some extra UV radiation from flares, you're always stirring it up. Is it possible that you get to a stage where the time scale for the response of the system, starts to play a role, you just get it to a different kind of solution, essentially a turbulent solution rather than the steady state plus fluctuation solution?
Yes. I mean, in a word, yes, that's possible. And it's borderline depressing that might be the case from the standpoint of the modelers. And in our own system, the solar storms and the CMEs, in our minds are roughly the equivalent of tsunamis, that brief but intense energy input to the system. And the question is, does that completely change the shoreline in Indonesia, or is it more like just waves lapping up on the shore? But when you have constant tsunamis around M dwarfs, you could be in a constant turbulent state. So some of the models in our group, one of the MHD models, so not even some, one of the MHD models does have a time-dependent mode. And there's some suggestion that this time-dependent mode can be validated, but that's only currently being validated for quiet conditions, not strongly disturbed conditions. So what they've done is they've taken Mars and rotated it on its axis through a day. And those crustal fields then rotate in and out of view. And they've run their model in steady state for 12 different positions of the crustal fields and just not rotated Mars at all. And they've gotten one answer from their model. Then they've taken the time-dependent mode of their model and run it through a day. And they showed that these results agree to each other within 5%. But that's a long time scale compared to solar storm energy input, which can be on the order of an hour or hours for flares. And so I still think we have a long way to go to be able to simulate these highly active external conditions at end dwarfs. But yeah, there's a lot of work to do there.
Yeah, thanks.
Okay, any final question? In which case then, Dave, thank you very much again. It was a really interesting talk and a very nice discussion afterwards. So on behalf of everyone, thank you very much.
Yeah, thanks so much for having me. And it was good to see a couple old friends here and hear from some people whose names I know in the literature and get to talk with all of you.
Okay, so as we mentioned in the emails earlier, we're going to sort of try out our second sort of social kind of breakout room discussion afterwards. So if you have time and you'd like to stay online, then please do so. If you need to leave, then